Hi. In this video, we've looked at vector component form. We've looked at introducing vectors, adding them together. Now we're going to be looking at um, breaking them into their components. So in the last video, we talked about how we resolve these into components using trigonometry. So the horizontal component, v sub x is equal to the magnitude of the vector times the cosine of the angle from the positive x-axis, and the vertical component of the vector is going to be the magnitude of the vector times the sine of that angle from the positive x-axis. We also talked about the total length of the vector being given by that Pythagorean theorem. So now what we're going to do is we're going to work with those components. So let's look at a couple examples here. The first one says a vector has a magnitude of 425 meters that forms an angle of 36 degrees and 10 minutes with the positive x-axis. Let's give the magnitudes of the horizontal and vertical components of the vector. The first thing I always like to do is to draw a picture of what I'm dealing with here. So I'm going to go ahead and do that. Go ahead and draw our axes here. And I'll illustrate this vector always from the origin, and we're going to go out 36 degrees and 10 minutes here, about there. So this angle is theta, and the magnitude of that vector is 425 meters. So essentially, we're looking at breaking this up into two components. V sub x, that's going to be here, and these are scalar quantities. So just the length of the horizontal component and v sub y, the vertical component. We can use those relationships above to help us out, but they should be pretty intuitive. So v sub x is going to be 425 times the cosine of that angle. Now remember, when we are looking at this angle in degrees and minutes, we might want to convert that over to decimal degrees. So 10 minutes, we would find that by taking 10 over 60, because there's 60 minutes in a degree, and we get 36.16 repeating degrees. V sub y is going to be the magnitude of that vector times the sine of that angle. So I'm just going to use my calculator to compute these. When I take 425 times cosine of 36.1666666, and remember I'm in degree mode, I get 343.104104.8. When I'm using significant digits, I noticed that 425 is given to three significant digits, so I'm going to round this to three significant digits, and I'm going to get 343 meters. Now I'm going to be looking at the vertical component, so 425 times sine of that 36.1666666, and I get, for this one, 250.807, and so on. So if I'm rounding that to three significant digits, 251 meters. So these would be my components when I break them up. All right. So it's nice to resolve these into components, because we can tell how far each of the cardinal directions that we travel in. Let's take a look at another example here. Clear this out. And here we have a vector with horizontal and vertical components. We want to find the magnitude and the angle of that vector. So notice that, again, it's really super important that we draw this one. So it says the vector has horizontal component of 2 square root of 3, and it has vertical component of 2. So those magnitudes are positive, respectively. But theta is in quadrant 3. So I'm over here in quadrant 3. That's where my theta is. Need to find theta. My v sub x is going to be a bit bigger than my v sub y. So here's my v sub x. And here's my v sub y. So my theta goes right over there. And I want to find the length of that vector v. So here is my vector v. I'm going to go ahead and write my lengths in here. Now, you might notice that this one has a ratio that we have been used to. I see a square root of 3 times 2, and I see a 1 times 2. So we should know that when we have a 30, 60, 90, we want to sort of look out for these. When we have a 30, 60, 90 triangle, these sides are in ratio of 1 to square root of 3 to 2. So in this case, my smallest side has a length of 2. My next size, it has a length of 2 root 3. So if 1 is to 2 and 2 root 3 is to root 3, so root 3 is to 2 root 3, then we would probably realize that we're multiplying by 2 to get these red values. So 2 times 2 is 4, and that's going to be the length of v. Now, you could also use the Pythagorean theorem for this, but I just think it's neat and more simple when we can see these ratios. So in fact, this means that the angle across from the smallest side is going to be 30. So that angle between the negative x-axis and that vector is 30 degrees. So we should know that the whole angle theta is going to be halfway around there, 180 degrees, plus that 30 degrees that we have. That goes a little further, and that gives us 210 degrees for a direction from the positive x-axis. So this would be our direction, and our magnitude would be 4. All right, let's look at one more example here. This will sort of hopefully put it all together. We're going to be looking at adding two vectors in this example and finding their magnitudes. So in this case, we're looking at a plane traveling a certain direction and then changing its direction. I'm going to go ahead and still keep listing this on the axes. That we're given, because that's the easiest way for me to write these. So we'll start out here with a nice picture. It says a plane travels 170 miles at an angle of 72 degrees. So that's going to look like this, roughly. Here's my 72 degrees. And my magnitude is 170 miles. Okay, then it turns to an angle of 41 degrees from the positive x-axis and flies another 120 miles. How far east and north has the plane flown in all? So remember, when we add those vectors together, we can either use the head-to-tail method or the parallelogram method. I'm going to try a head-to-tail method here. So what I'm actually going to do for this turn in the plane, I'm going to start on the head of the first vector, and now it's turning at an angle of 41 degrees, roughly like this, and it's flying another 120 miles. So when I put those together, when I add those vectors together, it's going to look like this. And I can find that red vector by finding the components for each of the blue and the green vectors. So that's what I'm going to set out to do now. So we remember our ratios. So for blue, v sub x is going to be that 170 times the cosine of 72 degrees. And the v sub y is going to be 170 times the sine of 72 degrees. For the green, when it makes a turn, the horizontal is going to be, let's call this W, is going to be 120 times the cosine of 41 degrees. But the vertical component of W is going to be, that's V, W sub Y, is going to be 120 times sine of 41 degrees. All right. So to find the red, we're going to add those together. We're going to add these together. So let's do that. Again, make sure you're in degree mode. I have 170 times the cosine of 72. And that would give me, it looks like I'm given two significant digits because 170 and 120, that zero doesn't really count. I'm going to start by listing them to three significant digits, and then when I add them together, I'm going to round to the nearest two. So I'm going to start out, this one was 52.5 roughly, and then it's going to be easier for me to just change this to sine. So if I'm looking for v sub y, that's approximately 161.6, so 162. Now I'm going to use 120 times the cosine of 41 degrees. And when I do that, I get approximately 90.56, so 0.6. We'll add those up in a minute. And when I change that to sine, I get about 78.72, so 78.7. We'll add these up. So I'm going to add these up, and I'm going to round to the nearest two significant digits. So when I take 52.5 plus 90.6, I get 143.1. So this is approximately 140 miles in the horizontal direction. And then I'm going to take 162 plus 78.7. I get 240.7, so that's approximately 240, rounded to two significant figures, miles. So I can tell that plane totally went 140 miles, about 140 miles to the east, and then 240 miles to the north. All right. That concludes our discussion on vectors. Hope it's helped.